Welcome to another How Do You Know, episode 85 on brown dwarfs. We sometimes do a series of programs on a planned basis on the Roche effect or the rings of Saturn, various things. This is our third program on planetary formation, and it's been more organic. One interesting idea leads to another. But first, this program, of course, brought to you by the Explore Scientific Company, all your astronomical and outdoor needs, and Star Mentor. If you've got someone on your holiday list this year who's new to astronomy or asking for a telescope, be sure you pick up a copy of Star Mentor for them. We all want everyone to enjoy the gifts we give, and with astronomy and telescopes and binoculars and observing the sky, the more knowledge you bring to the eyepiece, the more value you take away, and Star Mentor will be your guide on an exciting journey exploring the sky. In the news this week, NASA's OSIRIS-REx TAGSAM capsule is stuck. This is what they call an embarrassment of riches. NASA had hoped that the TAGSAM, the touch-and-go sampler on the OSIRIS-REx probe, after its 7-year journey, would bring back maybe as much as 60 grams of material from asteroid Bennu. They've already collected more than 70 grams from the outside of the capsule. Kind of amazing but true. We found out a lot about asteroids when the OSIRIS-REx touched down on the surface of asteroid Bennu, because even at less than 0.5 meters per second, the probe arm of the spacecraft sunk more than 50 centimeters deep into the interior of the asteroid. Bennu is a rubble pile asteroid. It's not a rocky or stony object. It's not a single object at all. It's simply a collection of things held together by their own very weak gravity. Well, they got more than 70 grams of dust and rocky material on the outside of the capsule, and it sounds like an interesting design. The closed capsule is held shut with 35 fasteners. If you've ever had to take something apart and gone, gee, another bolt, another screw, really? Well, yeah, NASA kind of over-engineered this one. Now the problem is they have 2 fasteners, 2 Allen head type screws that they can't get loose. Now, if you or I were working in the garage, we just get a bigger wrench. Put a hammer on that bad boy. Yeah, we'd do that. We might know a technique called using a breaker bar, basically a wrench extender. NASA doesn't have that option. Why? Well, the TAGSAM capsule is inside basically a nitrogen tent. They've got a glove box where you can reach in and manipulate with gloves and use tools, but this small transparent enclosure is basically constant flow of dry nitrogen is being pumped over the top of the capsule and the sample to make sure Earth's atmosphere with oxygen and water vapor and goodness knows what else doesn't contaminate anything. The problem is their box is pretty small and compact, and they're having trouble finding tools that are big enough to get them enough torque to break the fasteners free, and they have to have things which will fit inside the box. So they're working on it. I'm sure they'll come up with a solution. The folks at NASA are outrageously clever. I have every confidence in them. But if you ever struggle to get that last nut, bolt, or screw off of something, you know exactly where NASA is right now. The other thing that just fascinated me, Voyager 1 and Voyager 2, some of NASA's earliest I think they were the first multi-planet probes, and they're certainly the first interstellar probes, since they're now outside of our solar system entirely. They were launched in August and September of 1977, just a couple months after I graduated high school. It's almost 50 years ago. And they're now getting an over-the-air software update. like a brand new electric car, like a Tesla. I don't know. I don't think certainly they weren't planning on this long of a mission lifetime for Voyager. Same thing with some of the rovers on Mars, which they hoped for 90 days and they got 10 or 11 years out of them. I want NASA to build my next car and my next smartphone because these things just keep going and going. We're also happy to tell you about Explore Scientific's Certified Pre-Owned program. If you're looking for a telescope or binocular this Christmas and you're on a budget, or you're perhaps looking to go something one size bigger, one bit more magnificent, and you're wondering if you can afford it, I'm encouraging you very strongly to get a hold of the customer service desk at Explore Scientific. Would you like a 10-inch Dobsonian telescope for $550 plus tax and shipping? We've got them. We've got a couple of them. There are 2 in inventory right now that I know of. But if you're interested in high-quality binoculars for birding, hiking, hunting, astronomy, lots of those in the CPO category. We've got all kinds of goods in the CPO, and the quantities are very limited, folks. And I can't say it'll be here tomorrow, but I can say if you call and ask, the nice folks in the customer service department will have all the information for you. So check on that. Let's talk about brown dwarfs. And unlike the Disney movie, the proper plural is dwarfs, not dwarves. Dwarves are people, perhaps, but dwarfs are stars. And when we talked about brown dwarf stars, some of you, if you had an astronomy class, you may be familiar with what's commonly known as the HR diagram, or the Hertzsprung-Russell diagram. This is a diagram of main sequence stars. This is fascinating because in 1911, Einar Hertzsprung, and I dearly hope I'm saying that correctly, and Henry Norris Russell both came up with this idea of mapping stars by luminosity and temperature. And they came up with this lovely curve along which all the stars known fell. And this is now known as the main sequence. And there's been a lot of research done on this over the last century. But the HR diagrams kind of starts off, and it's up there on the screen. In the upper left are the hottest stars, the blue supergiant and blue giant stars. And then we go down the main sequence. We hit the yellow dwarf stars, which are like our sun, and then orange and red dwarf stars. And we always wondered, gee, if it goes along the spectrum from blue to red, could there be infrared stars? And people spent a lot of time looking for them, but very, very difficult to find. And you have to understand that when we're looking at this, and Hertzsprung and Russell and astronomers through most of the 20th century were looking at this diagram, the idea of an infrared star seemed perfectly plausible. When Hertzsprung and Russell came up with the diagram in 1911, nobody knew what powered stars. The whole idea of nuclear fusion hadn't been thought of yet. And so we knew what didn't power stars, but what did, it was a great mystery. And that, of course, came through atomic physics in the 1930s. But it turns out that when we look at brown dwarfs, they're not indeed true stars. True stars, and again, this is an evolving definition because astronomy is an ancient science. True stars, today we consider stars that are powered by some form of nuclear fusion. In its simplest form, as in our yellow dwarf sun, we have a core at the center of our sun where the temperature and pressure are great enough. The temperature reaches about 10 million degrees Celsius. And at that temperature, there's enough temperature and pressure from gravity that 2 hydrogen atoms, when they meet, they can overcome their electric repulsion. The nuclei can fuse and form helium atoms. This is a multi-step process. It's not quite as simple as I'm describing right now. But the idea of fusion, taking smaller nuclei and essentially welding them together to make larger nuclei and release a great deal of energy, this is the process that separates true stars from failed stars and protostars. If we're going to say star today, we mean that it's powered in some sense by fusion. There's more different kinds of fusion. Most stars are powered by hydrogen fusion. Some, such as red giants, are powered by sometimes by helium fusion. And the fusion cycle goes all the way up. And you've probably heard this on the How Do You Know program before. Stars can fuse elements up to iron. They can produce elements up to element number 26. But when you get to iron, each step of the process, you get less and less energy out. The fusion cycle for that next step takes much, much less time. And the last fusion state producing iron can last only a few hundred or at most a few thousand years before that fuel is exhausted and the star collapses and dies. However, brown dwarfs are completely on the other end of the scale. Brown dwarfs are an intermediate state between the largest planets and the smallest red dwarfs. Now you say, gee, how big do you have to be? And this idea kind of follows along with the idea we've discussed before, that a planet's mass and composition determines its characteristics. It's the same with stars. And if you're going to have real fusion in the core of a star, you have to have enough mass so the gravitational compression generates enough heat to kick off and ignite that star and start the fusion process going. So it turns out that brown dwarfs are too small and too cool they're too cool for fusion. That sounds crazy, but there you go. Now, when we talk about the mass of an object and how it determines what the object is and what its character is, for stars, this is known as the Vogt-Russell theorem. Again, Henry Norris Russell, and I think it was Eugene Vogt. I'm gonna back up and look that one up. But the Vogt-Russell theorem basically says that it's the mass and composition initially that determines everything about its star, its lifetime, its mode of fusion, how it will die, what the stellar remnant will look like afterwards. For planets, it's looking like much the same, something very similar as the Russell-Vogt idea is going along here. And if we talk about a brown dwarf, the maximum mass, and again, this is not by seeing thousands and thousands of brown dwarfs and seeing what's the smallest or largest one we could find. This is all based on theoretical mathematical modeling. And 0.08 solar masses or 80 Jupiter masses is essentially the maximum. If you get more than 80 Jupiter masses or 0.08 or 8% of a solar mass, you've got enough to ignite that fusion reaction in the core, and oh boy, you're a real star. Now, real stars, true stars, do give off heat and light, and so do brown dwarfs. What's the difference? The difference is that for a real star, with a fusion process going on in the core, it is that fusion process which produces the heat and light that the star gives off. For a brown dwarf, that's not true. There's no energy generating process at the core. Instead, what you've got is something that's gotten really hot because it was squeezed really hard. Pressure creates heat, and we see this everything from glaciers to ice skating. When you get a lot of pressure, you generate a lot of heat. Now, that heat isn't retained. When you have something hot, like a cup of coffee or a bowl of soup, sitting on the table, it loses heat to its environment. I'm sure we've all picked up a cup of coffee and taken a sip and gone, oh, it's cold. Well, in fact, that same thing happens with a brown dwarf. It has a certain amount of heat from its creation process. This gravitational compression of gas and dust, brown dwarfs are essentially the same composition as a Jovian planet. Some hydrogen, some helium, some lithium, and a smattering of other elements, a very small percentage. These things get compressed, they get hot, and brown dwarfs then lose that heat by cooling off to their environment, losing heat to the environment over time. Now, if you have a real star, because you have not only an energy producing process at the core, but you have nucleosynthesis at the core. Stars are using fuel, creating new elements, and so a star's composition changes over time. If you have a large enough star, you'll go through several different kinds of fusion before you reach the end state and the star dies. Well, with a brown dwarf, none of this ever happens. They have as much heat as they're going to have when they first form, and then they just slowly cool off over time. Now, they had speculated that brown dwarfs existed. They were called infrared stars back in the day. And the first mathematical prediction of an actual brown dwarf or infrared star goes back to the early 60s. And from the 1911 creation of the HR diagram to the 1960s, that 50 years, tremendous explosion in knowledge about nuclear physics and fusion processes and all sorts of things. But brown dwarfs were not discovered until 1995. It was a Spanish team, Rafael Rebolo, Maria Zapatero, and Eduardo Martin. And these three astronomers located the first brown dwarf from an observatory in the Canary Islands. Their first brown dwarf, called Teide 1, and again, I'm not sure I'm pronouncing this correctly, I'm giving it my best, and they named it after their observatory in the Canaries. But this first brown dwarf was located in the Pleiades. It was about 400 light years away. And we know a lot more brown dwarfs. We've cataloged thousands since then. And currently, the nearest brown dwarf is just 6.5 light years away. And it is the third closest star system to us. Proxima Centauri is about 4.3 light years away. Barnard's star is just under 5 light years away, and then this brown dwarf, Teide 1, about 6.5 light years away. Why were these so hard to catalog? As stars get smaller in mass, they get obviously smaller in size. It turns out that if you go from a Jovian-sized planet to a brown dwarf of 80 Jupiters, the radius of the planet doesn't increase very much. The additional mass, remember these planets are mostly gas, and so the additional mass, you add more mass, you compact the gaseous and liquefied interior more. It doesn't increase in size very much. So think about trying to find a Jupiter that's light years away. You're looking for a very small object at a great distance. The other thing, of course, brown dwarfs primarily radiate in the infrared part of the spectrum. Their primary source of radiated light is heat, infrared light. And infrared is hard to use. It's hard to use an infrared telescope on Earth. There's a couple reasons for that. One, our atmosphere, our nitrogen-oxygen atmosphere, absorbs infrared light pretty well. We also live on a water planet. 70% of our planet, give or take, is covered by water, so there's always substantial humidity, and water is a tremendous absorber of infrared energy and heat. If you paid the energy bill for heating an outdoor pool, yes, you know exactly what I'm talking about. Or if you're like, oh no, we'll wait for the sun to warm our pool. Wow, it's been sunny and hot for days. Why isn't our pool much warmer? Well, water can absorb a great deal of infrared energy. The result is that trying to look for an infrared source on Earth is really, really difficult. The Canary Islands gave these astronomers a high-altitude observatory where they could do that. Now, of course, we have a couple of infrared space telescopes. There's the WISE, which is the Wide-Angle Infrared Survey Explorer. And, of course, the new kid on the block, the James Webb Space Telescope, which is primarily an infrared scope. And stars, of course, and brown dwarfs follow that pattern that we've talked about before. The smaller it is, the more common it is. So we think there are more brown dwarfs in our galaxy than stars, somewhere between 25 and 100 billion brown dwarfs in our galaxy today. That number is a mathematical modeler's, that comes from a model, not from observation, friends. And it's often true that when we start looking for things and we say, oh, we expect to find this many, we find out that there's more than we first thought. This is true with asteroids, stars of different types, galaxies, and we're constantly getting knocked on the head by this idea. You may remember the Hubble Deep Field photograph. Hubble Space Telescope was pointed to an area where there was nothing there. And they said, let's just point it and leave it open. I think they left it open for about 100 hours. And the photograph revealed some 50,000 galaxies. And people were stunned. Wow, there's that many? Yes, they're just very far away, very faint, and hard to detect. We've also found that these brown dwarfs are really highly magnetized. That shouldn't surprise us much. Jupiter's magnetic field is 1,000 times greater than Earth, and we've realized since that was discovered by the Voyager spacecraft, we've realized that the interior of Jupiter is a lot of metallic hydrogen. It acts like a metallic core. It spins like a dynamo. It generates a tremendous magnetic field. And we think that brown dwarfs, which are even bigger, have even more magnetic energy than a Jovian planet. They're also radio bright. Like Jupiter, they give off lots of radio wave energy. And so we look at this as not a star, but a star-like object. We might have said quasi-stellar, except we used the term quasars before. And those aren't stars either. Those are active galactic nuclei. And we know right now that brown dwarfs start out with a surface temperature of about 3,000 centigrade. That's the hottest they get. Keep in mind that these things are the hottest that they will ever be at the point of their creation, and they slowly radiate away their heat, and the surface temperature drops over time. You can see there's a lovely diagram up there, and it shows you, here's our sun, which is a yellow dwarf, and then it shows you a red dwarf, which is very small, about a tenth the radius of our sun. And then you see brown dwarfs and Jovians, and a lot of these brown dwarfs are quite small. They literally are the size of a Jovian world, and now they've been given spectral class Y. So if you remember your spectral classes from astronomy, O, B, A, F, G, K, M, you can now add Y to that. And we know that they are similar in composition to a Jovian planet. Interestingly, one of the ways to tell, is it a brown dwarf or not, is to look for the presence of lithium. Why? Lithium is a fusion precursor, and so when you have a normal fusion-powered star, lithium is consumed very, very quickly. And unless you're seeing a absolutely new minted star, you're not going to see any lithium there at all. That's consumed. But if you find a lithium spectral line in a small object and you're not sure, is it a red dwarf star or a brown dwarf? If you've got lithium, you almost certainly have a brown dwarf. Now, what's interesting is that this cooling process that goes on over time, it actually changes the composition of the surface of a brown dwarf. Now, we know stars change over their lifetime, but they change from the core out. It's the core that changes as fusion progresses. However, with the brown dwarf star, what happens is as they cool, new elements and new minerals and things are able to form as the temperature drops. So when a brown dwarf is newly minted to about 100 million years old, sounds like a long time for you and me, but not for a brown dwarf, then their surface composition is essentially identical to a red dwarf star. And they have compounds like titanium oxide. We use that in paint to make white paint. And carbon monoxide are found in the stellar atmospheres. Between 100 and 500 million years old, they get cold enough that silicate minerals begin to form. And they get silicate minerals such as enstatite and quartz. Now, I've never seen enstatite, but I've seen quartz often enough. And these minerals start to precipitate out of the atmosphere and they form clouds. So you can actually get clouds made out of quartz particles condensing from the atmosphere, much as water droplets condense from our atmosphere to make clouds of water vapor. You get clouds of quartz vapor. From about 500 million to 1.5 billion years old, the silicate clouds are getting colder. They're coagulating into larger and denser particles. And these clouds break up and they sink into the interior. Methane and ammonia at this stage start forming, and they dominate the upper atmosphere. And you actually get water forming in the atmosphere of older brown dwarfs. And now you get an atmosphere very similar to Neptune and Uranus, basically ice giants with methane ammonia atmospheres and CO2 and water ice clouds. And we know that these things can get as cold. Some of the coldest ones, surface temperatures are actually below 0 degrees centigrade, if you can imagine that. Now, how do these things form? And in last episode, number 84, Professor Mark Makorian, he said, we're breaking physics. I don't like that phrasing. It's too spectacular for this old astronomer. But certainly finding things that lie outside our current theory and system of knowledge is very exciting. And Professor Makorian said, gee, we're breaking physics because they found Jupiter mass binary objects in the Orion Nebula, what they called jumbos. And they're like, wow, nebulae like these should make stars, but they shouldn't make planets. And if you've got Jovian mass objects, yes, you have planets. And this is really interesting, but the question is, well, how do we make a brown dwarf? And the idea of how to make a brown dwarf, no one's actually sure how they form, but there's a number of very interesting theories. And let's take a look at some of those. Now, we know that in a nebula like Orion, which is a nebula, a molecular cloud, it contains hydrogen, it contains helium, it contains dust such as carbonaceous granules, silicate granules, and other molecules, and gravitation causes this dusty gaseous cloud to compress. We've talked about this before. As clouds compress, they heat up. When gases gets heated, they want to expand, and so you can get this equilibrium where a star cannot form. It's the dust particles which are the secret sauce, which allow smaller stars like our sun and red dwarfs to form, because these dust particles have tremendous surface area and they're able to radiate away the heat, and so the excess heat from the outer atmosphere is radiated away, allowing everything to be more compact. Now, if brown dwarfs and jumbos are formed in the same way, it's just different amounts of material, the question is, what makes them stop? The idea of what makes a molecular cloud collapse is quite simple. You simply have a local area which is denser than the surrounding areas, and its self-gravity causes compression and collapse. So far, so good. But if you're in a relatively dense area, and I say relatively, thinner than a vacuum most laboratories can pull on Earth, nevertheless dense for interstellar space, if you're in an area with a dense nebula and it starts to collapse, why does it reach Jovian mass or brown dwarf mass and stop? Why doesn't material continue to infall and collapse? Why doesn't it keep drawing in material? And why doesn't it run all the way up into at least a red dwarf star? Now, when it comes to Jupiter mass objects forming around a regular star like our sun, we have a pretty good answer for that why does it stop question. If you've taken a look at this idea before, if you have a protostar, there's a lot of material swirling around, and the rotation tends to compact everything as a disk. And so you get this dusty gaseous disk that surrounds a star along its equator, and it orbits and it rotates, and the collapse of the disk, pancaking it, basically squeezes things together and helps planets form. Why do we go from a terrestrial planet to a Jovian? It's simple. At some point, the core gets large enough that the star can start to hold helium. We can't hold helium. In our atmosphere, Earth's gravity isn't strong enough. If you let a helium balloon go, the balloon will rise up, lower pressure, it will expand, it will pop. The balloon falls back to Earth. The helium is lost to our planet forever because the helium will keep ascending to the upper atmosphere. The gravity is not enough to hold it. The sunlight will hit it and energize it, and it will be driven off into space, and we lose that material forever. Now, so far so good. But if a planetary core continues to grow at somewhere between 2.5 to 5 Earth masses, the core gets large enough that you can actually start to hold helium. Why is that important? This dusty disk of material surrounding a young star is full of hydrogen and helium because that's what was in the cloud that made up the star itself. And if you're not big enough to hold helium, then you're just swimming through it. Once you get big enough to hold helium, it's like instead of putting a net outboard your boat, if you're going along in a boat and someone's skiing behind you and you put a net in the water, well, the net will flow through the water. Excuse me. The net will flow through the water, and it doesn't hold any water. It doesn't trap any water. But if you put a plastic trash bag overboard, well, that trash bag holds the water, and wow, the drag is much greater because now you're collecting water instead of just having it pass through a structure. Same thing happens when a planetary core gets large enough. First, it gets large enough that it starts to capture the helium. It doesn't just swim through it. It starts to capture the helium. As it does, the atmosphere grows, and doesn't take too long before now the entire mass, and remember, the gravitational pull of a planet has to do with the mass not only of the core, but also the atmosphere surrounding it. When the helium atmosphere gets large enough, now you're large enough that you can hold hydrogen, which is the most abundant element in the universe. And once you're large enough to hold hydrogen, surprise, surprise, you've now reached a point where you're holding a big trash bag overboard and you're collecting a lot of material. And so in a very short order, the planetary mass can grow very large indeed. Why does this process stop? At some point, the protostar at the center of that system ignites. The fusion process kicks off, and when it does, the star suddenly becomes very energetic. It's giving off a lot of radiation. It's giving off a very powerful solar wind of ionized particles and radiation, and essentially the dust and gas that the planets are feeding on, if it's light enough, is being driven away. What gets driven away first? Hydrogen and then helium, the lightest atoms out there. And so when a star ignites, it blows off all of this gaseous material from its dusty disk, and planet formation slows way down. Jovian planet formation comes to a crashing halt because there's no more abundant hydrogen and helium to feed on. So we know how a planetary mass stops growing in a standard star system, but what happens in a dense nebula like M42? Well, we have a couple of ideas. First of all, how do they collapse at all? One idea is that they may form because of local shock waves. We know that places like the Orion Nebula are stellar nurseries, places where new stars are forming. When these new stars form and they ignite, as I said, it's like a blast going off. It goes off in all directions in space, and it blasts that material out away from it, stopping Jovian-type planetary formation. But if you're in a dense neighborhood like the Orion Nebula, you're going to create a shock wave of material blasting outward, and that shock wave can run into molecular clouds and help compress them. So why do the brown dwarfs stop forming in a rich, dense environment? One thought is that you may be dealing with gravitational ejection. In an area like the Orion Nebula, we know that as stars form and become compact, not only do they clear a bubble in their own neighborhood, but they interact gravitationally and they kick each other out of the nursery. So these stars interact gravitationally and they slingshot away. That's why we see evidence of our local star group is expanding, the Pleiades is expanding, the double cluster is expanding, and we see all these new clusters of new stars where the stars are slowly moving away from each other. So brown dwarfs could be smaller objects, and somebody played crack the whip with them and they were ejected from the nebular cloud neighborhood and they stopped growing that way. Keep in mind here, friends, we know that about 85% of all stars exist in a multiple system. We talked about this last time. And when you have a multiple star system, we know that, in fact, wow, you eject a lot of material. The other research that just came to light, I didn't have time to add it to the program. This just came out in the astronomy press. Basically, there's a research study now that says in a binary system, consider this the polar axis, this the equatorial axis, if the equatorial axes are tilted, one with respect to the other. This is a prime environment for gravitational ejection of planets. So if you have two binary stars and we think, oh, they must both be orbiting with their poles aligned and they're going around like tops on a table. Not always true. We know that binary stars, many of them, have axes which are tilted with respect to each other. You think about it, the axis of a star, the equator is at 90 degrees to that. The dusty disk of material where planets form is at 90 degrees to the equator. And so if you have two stars orbiting each other where the axes are at angles, then in fact the two planetary disks can intersect, and these kind of systems can eject a lot of planetary mass. And if we're having binary systems with brown dwarfs forming, that could be a mechanism that stops the brown dwarf from growing because it's ejected from the binary system. So we have a number of ideas here, but no real data. This harkens back, this reminds me of the time of the mid-60s to early 70s in the 20th century, when people were arguing about how did the moon form. And we had lots of different theories. We had a theory that, oh, it was a fission theory, one blob of material that split. We had a capture theory where the moon was made somewhere else. We had basically the fission theory where the proto-Earth spun too fast and a chunk was spun off the surface. The theory nobody liked was, oh, maybe a big planet hit the Earth and the splash of material ejected into orbit made our moon. It turns out that the other three theories were definitively rejected. They didn't make predictions that matched what the Apollo astronauts brought back from the moon, and also they did not meet standards. They weren't predicting successfully, or models proved that they were physically impossible to do. So right now we've got these multiple theories of how brown dwarfs might stop before becoming a star. We haven't got enough data to really test these theories and definitively say, yeah, we can eject this one or that one, much like a planet being ejected from a gravitational system. Of course, what do we want when we have multiple competing theories? We want more data. When do we want it? Now. Unfortunately, we have to wait. I know, it's frustrating. The wheels of science do grind slowly, but they are sure and irresistible. Sometimes we're waiting for new technology, such as a new space telescope. Hello, James Webb. Sometimes we're looking for a new idea. Hello, Albert Einstein and relativity theory. Sometimes we're looking for both. And so we've gotten some new data. Both the Hubble Space Telescope and WISE, the Wide Angle Infrared Survey Explorer, the first infrared space telescope, they've studied a lot more brown dwarfs than Webb has. Webb is a relatively newcomer on the block. We're expecting great things. But Hubble and WISE have found that virtually all brown dwarfs have circumstellar disks just like protostars. No real surprise there. If protostars form dusty disks, why wouldn't brown dwarfs? There's a strong indication that our planet Jupiter, in fact, had a dusty disk. Is Jupiter a proto-brown dwarf? Well, there's excellent evidence that the 4 Galilean moons, which are all similar in composition, and they vary quite nicely in density, getting less dense as you move away. They look just like a planetary system around a star. So when we're seeing these dusty disks around brown dwarfs, did Jupiter once have a dusty circumstellar disk? Yes, I think it probably did. And what we're looking for is, gee, if these brown dwarfs have dusty disks and there was no stellar ignition to blow away that gas and dust, well, gee, brown dwarfs might in fact have planetary systems with quite large Jovians. Gee, it might even be possible that brown dwarfs form in binary pairs because there's no stellar ignition to stop the formation of a second planetary body going from planet size to brown dwarf size. So there's all this information that says brown dwarfs may in fact actually be failed stars, stars that just didn't ignite and complete the normal developmental cycle. Or if you prefer, brown dwarfs have an alternate developmental cycle which favors binary systems with pairs of brown dwarfs or a brown dwarf with large Jovians. Again, what's the most common or likely or realistic scenario? Nature will tell us. We need more data to take a look and find out. As I said, Jupiter may be in fact the nearest brown dwarf. Where's the dividing line between planet and brown dwarf? Jupiter contains what we call heat of formation. It had an amount of heat from its initial compression and formation, and it's slowly cooling off over time. It's giving out light in the infrared spectrum. It gives off radio frequency energy because it has a very strong magnetic field and dynamo system. And when we look at this, we go, wow, okay, where's that dividing line? People ask, what's a planet? Is Pluto a planet? Well, here's the other end of the spectrum. Is Jupiter a planet? Where's the dividing line between Jovian planet and brown dwarf failed star? This is an evolving question. We're going to have to see more data. My point of view, friends, I think that in fact what we'll have is an expansion of the Russell vote. The Vogt-Russell theorem. Vogt came first, by the way, by about 10 years. The Vogt-Russell theorem says that everything about a star is determined by its mass and its original composition. I gave you Barth's corollary last week that a planetary system is fully determined by its mass and composition at its formation. And I think we're going to see that this planet brown dwarf star is more of a spectrum than a distinct dividing line. If there is a clear dividing line, there is for planets. If it's large enough to crush itself into a sphere, if it's hydrodynamically stable, then it's a planet. Its mass and shape and nature determine what it is. Artificial dividing lines, this is a planet, that isn't. No, the object itself, its internal physical properties will tell us. I think we'll probably find that for brown dwarfs and Jovians, there may in fact be a natural dividing line which says, aha, planets end here, brown dwarfs start there, and maybe we're looking at the dividing line between planet and brown dwarf is, are you big enough to collect a helium atmosphere? We'll see. These ideas are evolving over time. Now, when we look at evidence from Hubble Space Telescope, we've got other interesting evidence about brown dwarfs forming in binary pairs. Hubble discovered a binary pair in the constellation Ophiuchus. A lot of you know Ophiuchus. It's up near Gemini, very beautiful. And they discovered a pair of brown dwarfs that they named Ophiuchus 98AB, being the A star and the B star, except they're not stars, they're brown dwarfs. And these are a pair of brown dwarfs with a mass of 15 and 8 Jupiters, respectively. Remember, 80 Jupiters is the cutoff line where fusion starts. These two objects are 200 AU apart. That's a tremendously wide binary pair. If you think of the Sun and Jupiter, if you want to think about Jupiter as a brown dwarf, then our binary system, they're 5 AU apart. Pluto is 40 AU out. The Kuiper belt around 50 to 100 AU out. These pair of brown dwarfs are 200 AU apart. We've talked about this on the program before. There's something called the Roche limit. There's not just a Roche limit of how close can a moon get to a planet before gravity destroys it. There's an outer Roche limit. How far away can you get a moon from a planet before some accidental tug from the star or another nearby planet pulls it away from the orbit of its parent planet? The amount of energy it would take to extract a moon or a planet from orbit around a parent body is called binding energy. And this pair, Ophiuchus 98AB, they have the lowest known binding energy of any system we've discovered. That means that, the slightest tug from a passing nearby star would separate the pair into two independent objects. This is really interesting because scientists quickly realized, the astronomers looked at this and said, they couldn't possibly be a binary because they captured each other. They are so far apart. The binding energy is so low that it would be virtually impossible for them to come and, with their mutual gravitation, fall into orbit one around the other. Their approach to each other would have to be so slow and so perfect, it would be trillions to one against the odds of such an event happening, which means they had to have formed together. Now, we know that planets in systems change their orbits. We know that periodic tugs, like pushing a child on a swing, can change the height at which they swing. We know that periodic tugs from gravitation of planets in a solar system can cause them to fall in or move outward. And so we're looking at this and saying, gosh, were there other things in this system and these two got pushed apart? We don't know. We need more study. And of course, the newest class of brown dwarfs are what they call Y class. These are the oldest known brown dwarfs, the Y class. And they have surface temperatures from 175 down to minus 25 centigrade. For the Americans in the audience, 175 C is about 350. That's where you put your casserole or your pizza in to bake it. It's a moderate oven. Minus 25, yeah, that's really cold. That's a really bad day. If you're out in minus 25 Celsius, that's a really bad day. And by comparison, Jupiter's surface temperature, minus 148 Celsius. Why is Jupiter colder than a brown dwarf? It had less heat of formation. Less material fell in and compacted, so it generated less heat, and so it didn't have as much to begin with. So its temperature today is quite small. Well, the interesting thing is they can now use light curves and they can map these brown dwarf surfaces from light years away. It's kind of crazy. We know that on Jupiter, its magnetic pole is not aligned with its physical pole, and so we can see the magnetic pole, which originates in the core. We can see how it goes around, and we can map the core speed versus the surface speed, and the surface is moving faster than the core, and that's another show for another day. But when they use this phenomena, they get light curves coming off in infrared, coming off the surface of these brown dwarfs, and perhaps surprising, perhaps not, they have belts which are dark, cooler areas, and zones, which are lighter areas of rising material. They have spots, which are probably storms, like the Great Red Spot. They map out to look very much like Jovian planets in our own system. And we take a look at this and we find these tremendous magnetic fields. They're so powerful. That's what lets us use them kind of as a flashlight from the inside of the brown dwarf out to map these surface features. And we're finding they're very like our own Jovian planets. Should we be surprised by that? I really don't think so, because when we look at Jovians, their atmosphere convex. Star atmosphere is convex as well, but they don't have the energy driving them from the inside out. And so you get different patterns of convection and movements of gas from the surface to the core and back out again. And I think it's really fascinating that brown dwarfs are kind of looking like giant Jovians. Where's the dividing line precisely? It's kind of interesting. And right now, we don't have enough research to really clearly say, aha, here's the boundary, here's where it lies. Well, that's all we have for you today on brown dwarfs, a fascinating subject and a lot of new information. Like so many areas on the cutting edge of science and astronomy, there are a lot more questions than answers, but that's what makes it fun. If you've got questions and you'd like to learn more, I urge you to go to the Explore Scientific website, download a copy of today's show notes, which also contains the illustrations and links for you to learn more, and go ahead and put it into your favorite search engine. Make your own search on brown dwarfs. If you have a particular question, you're welcome to email me at astronomyforeducators@gmail.com or drbat explorescientific.com. Thank you, everybody. We'll look forward to seeing you next week with another How Do You Know program.